Okay, so these are two examples from chapter 6, which is all about potential energy, kinetic energy, work, so forth. So the first example describes, let's see, I think we'll work in green. The first example describes the work done when a person, and we're going to pretend that person is right here, so you can draw a little guy if you like. So that's the free body diagram of a person. This person's walking uphill at a constant angle. And we're trying to determine the work done on a backpack that that person is carrying with them for this little trip. They're only going for a vertical height of 10 meters, so not too far. So what's the work done? Um, we're going to look at two different kinds of work done. First, we're going to look at the kind of work done that the hiker does on the backpack as he goes up, and then we're going to look at the work done by gravity on the backpack. So that's kind of two different things. We'll split it into parts A and parts B. Okay? All right, so let's see. So first we'll look at the work on the hiker. So first notice that the angle we're looking at here is in this way. So the motion that this hiker is going on is this motion right here. So let's just keep that in mind. Theta is not here in the triangle that we have. I drew that triangle for another reason, which we're going to look at in a sec. I think that's the only tricky part of this problem. Theta is along this axis of motion. So the axis of motion is slanted, if you will. So if you wanted to rotate that so that it looked like the person was standing here and there's no incline, then theta is kind of like this angle right there. Okay, I think that that's a little bit too much and can get confusing, so we're not going to rotate it. We're just going to look at it up there and keep that in mind. Okay, so remember that the formula for work is force times distance. This time the distance is not, we're not working, we're not exerting that force directly along the line of motion, so we've got to worry about the cosine of theta term in there, and it shouldn't be a big deal. Okay, so we've got that down. All we've got to do is plug in. The only question is they didn't give us theta. In this situation, we're just saying that theta is arbitrary, and we're supposed to somehow be able to calculate the work done. We do know that h is 10. Remember, this hiker is moving upwards vertically by 10 meters, not this way being 10, but upwards 10 meters. And I don't even think that theta really matters in that case, and here's why. It's kind of a neat little reason. So notice this d cosine of theta term can actually be reduced to something else. In fact, d cosine of theta, I'm going to have to relearn this, I haven't used it for a couple weeks, is equal to that 10 that we have. Now why? Why is d cosine of theta equal to 10? I think it's just a little bit of simple geometry. So go back to the triangle. Why did I draw this as a triangle? Well, I wanted to put the 10 in the right place. That was one reason. But another reason is so I could do just a bit of geometry. There's lots of ways to see this. Here's my favorite. Remember, you can always just think of an imaginary line up there. And if you imagine that this line is parallel to this one, in fact it's not an imagining, I've set them up to be parallel, then you have alternate interior angles. So the theta that you have right here is the same thing as this by alternate interior angles from geometry. So if those are the same, and then you look up here and you do the cosine, what is the cosine of this angle? If you're looking up here, then the cosine, oh my goodness, I think I need a mouse pad. Let's find one. Got it. Anyway, if you look up there, then the cosine of this theta is adjacent, or 10, over hypotenuse, and that is just the distance that he's actually walking. So they didn't give us that, so we're just going to call it d. And if you rearrange that, you multiply d up here, then you get d cosine of theta equals 10. That's where that came from. And what we wanted was d cosine of theta, so in fact the work simplifies to fh times 10. So we only need to figure out fh. Well, if you think about the free body diagram, this is something that should be familiar to you guys by now, then fh because of gravity, is going to be the exact same thing as mg, right? That's Newton's second law. If you do the sum of the forces equals mass times acceleration in this situation, then they should sum to 0. There's no acceleration in the y direction, so that's equal to 0. The two forces involved are Fh, and then mg from gravity is going down, so Fh equals mg. So you can just put mg right here, and we're going to say that this hiker weighs 15 kilograms. So 15 times 9.8 meters per second squared times the 10 that we just discovered because of that d cosine theta thing, and we get the work done by the hiker. It turns out to, when you do some significant figures, 147, and it's, oops, my mistake. Should have got my calculator there. So it turns out to, that was the force, 1470, and this is work, right? So our units should be joules. Newtons. Ha, that's a force. Okay, so now let's think about what work is gravity doing on the backpack. So that's kind of this way. So if we think about it, if you just think for a second, like I said, it's kind of this way. The work done by gravity, since gravity goes downwards, is kind of this way. So the new axis of motion, let's kind of get rid of some of this stuff I had for the first part. Person's still there, you remember. So this time, gravity axis of motion is going to be down that way, isn't it? So I don't think it's theta we're looking at anymore. In fact, the angle that gravity is pushing down with is now this thing, which is just the supplement, or 180 degrees minus whatever that angle was. So that's the new angle that we're working with. So when we go f d cosine theta, it's not theta anymore. It's this, right? When we're looking at gravity, it's going through this angle now. So cosine of 180 minus theta instead. So now the question naturally becomes, how can we work with this cosine of 180 minus theta? Since we don't know what theta is, that's a problem, right? Before, we were able to look at a triangle and come up with a clever relationship. And I'm kind of going to do a similar thing on this one. So can you simplify cosine of 180 minus theta? And the answer is yes. In fact, it's equal to negative cosine of theta. Why? If you've taken pre-calc, this is like cosine of A minus B, and you could use that identity for cosine of A minus B, and you'd get negative cosine of theta if you use the identity. If you haven't taken pre-calc, no worries, because you can also just think about it with quadrants. So if this is theta, then 180 minus theta is just the supplement over here, right? So that angle terminates in what quadrant? What quadrant's over here? Quadrant 2. And we're talking about cosine. Is cosine negative or positive in quadrant 2? If cosine is the x-coordinate, is x positive or negative over here? It's going this way, so of course it's negative. So there's another reason why that's true. That's like its own little identity. So you could use that identity, or you could think about just what quadrant you're in and cosine and so forth. So either way, this simplifies to negative cosine of theta. Now if you look at this part right here and compare it up to what we had before, doesn't that look almost identical? You've got a minus, so let's take the minus out in front. So you've got minus fg d cosine of theta, and then you say, oh my gosh, didn't we know d cosine of theta already? This is the theta that we're talking about from up here, so that part's just 10, right? So this part's just 10. And what is fg? Wasn't that just force of gravity? Just the same thing we had right here. So that's negative mg times 10. So now we've got negative 15 times 9.8 times 10. So that's just the opposite of what we had before, negative 1470 joules. This time it's negative, because gravity is doing negative work as you try to trudge up that hill. Okay. So that's that problem. I guess you might be curious about like the net work done, because we had two types of work working together. So let's go down here and let's say there was a part C. What if they asked you about the net work of the system from both of those other two works? Remember, anything when they say net is usually just a sum. Just like for forces in Newton's second law, we add up all the different forces. So we'd add up all the different works, which were this guy and this guy. And if you add them up, you get that they cancel out and become 0. So there's not really any net work done in this situation. Okay, so there's the first example. Let's go ahead and go look at another one now. So this example is quite a bit further in the book. This is after we've learned kind of what is potential energy, just a little bit about that. And I think something the book says that's really important when they're just done with their discussion of potential energy about is that, I think it's on page 146 in our text, but you should realize that potential energy, you're really worried about the net change in potential energy most of the time. For kinetic energy, you're usually thinking about, well, sometimes you're thinking about kinetic energy at a certain place in time because you're moving at a certain speed and you can just plug that speed in and get the potential energy. However, the potential energy is always defined usually in terms of some change in position, and it's usually defined in a vertical position, but not always. I mean, your spring might be horizontally situated. So the thing is, it doesn't matter how you get from point A to point B when you're doing net potential energy. It could be any kind of path. So I think a roller coaster is a really good situation, really good analogy for this kind of scenario. So let's say we had a roller coaster, and we could put any kind of movement in here possible. So we're going to look at points 1, 2, and 3 on this roller coaster. So we could do any kind of movement we want in here. We could go like this, and then it goes up to its maximum height, and then the roller coaster goes all the way back down, and it could go back up for a second, and then drop back down. The whole thing is the motion between those points doesn't matter. Whatever points you want to consider, I'm going to say we're going to look at points 1, 2, and 3. I could have picked more, but I chose to pick those. What the motion happens between those doesn't matter for potential energy purposes. It really doesn't. And you can also always pick different coordinate systems. So my coordinate system this time is relative to point 1. So you see how I've made the coordinate system have its origin at point 1. Could I have made the origin up here at point 2 or down here at point 3? Sure. That also isn't going to have a lot of effect on your situation. So that's what's nice about potential energy. Anyway, so let's think about 1, 2, and 3. So let's calculate the potential energy at point 2 and 3 if we're using the origin right here. Okay? So the potential energy at point 2 should be, this is gravitational potential energy, right? So it's mgy. And what is y? Y this time is at point 2. So what is that? Let's say that this time our roller coaster weighs 1,000 kilograms. So let's make it a nice round number. So 1,000 kilograms. G is just our old friendly constant, of course. And y2 from this coordinate system, it looks like I've measured that to be a positive 10, haven't I? 10 meters. So I should put some meters on here. Okay. So that comes out to, let's see, a calculator here, and it looks like if I put it in scientific notation, I get 9.8 times 10 to the 4th. And we're talking energy, so joules, right? What about point 3? What about over here? Now that's got a negative y, so it'll be mgy3, which is going to be 1,000 times 9.8. And this time it's down from the origin that we created, so it's negative 15. And that's going to be a negative potential energy, isn't it? So you're going to have a whole lot to look forward to in that case. It's up here. This is when you have a lot of action to look forward to, when you've got a lot of potential energy. Down here, you're kind of done with the ride, and the show's over. Okay, now the real thing I said earlier was that we wanted to focus on the change of potential energy. What's happening with potential energy as we change? And we'll look at some applets and stuff like that in class, or for homework, one or the other. So anyway, what's the change from 2 to 3? So as you go from here all the way down to there. What's the ultimate change of potential energy? Well, remember, when you say change, you should be using the symbol delta. So that's just the end 3 minus the beginning 2. So you just do those mites and subtract them from each other. So that'd be negative 1.5 times 10 to the 5th minus, what do we get, 9.8 times 10 to the 4th. And then, of course, that's also going to be in joules. You might expect it's negative since this was down farther. So notice, our potential energy went down a lot between those two, which makes sense. When you're up here, you have a lot of potential, a lot of stuff can happen. Once you've ridden the ride down to here, you've used or consumed, kind of, if you want to think about it like that, a lot of your energy. So potential energy's gone down by this much. Okay, now I want to ask the question. I said that it didn't matter where we located our origin. We chose to do it here before. Now let's erase that. And let's put our origin at 3. So I said put it relative to 3, and then let's just do the same computations and see what happens. In fact, I'm just going to draw a new path. I don't know what we had before, so maybe we had that before. Let's draw a nice path like this now. Except now our origin, you have to ignore my black lines, our origin is right here. Okay? So, what's the potential energy over here? That is up 15, isn't it? So we're going to do m g and up 15. I don't know what that is. Let's see. Calculator says 1.5 times 10 to the 5th. What do you know? There's symmetry in this problem, right? Before it was down that much, so it was negative. Now it's up that much, so it's the same thing but positive. That makes sense. What's the potential energy up here now? If we look at from here up to there is 15 plus 10, so that's 25, and it's positive, isn't it? So we're going to get a lot there. So that's going to be 1,000 times 9.8, and this time this is 25. So I got, let's see, 2.5 times 10 to the 5th joules. Okay, if we redo the change of potential energy from 3 to 2 in this coordinate system, what's the potential energy here? Since this is at the origin now, the potential energy there is now 0. What's the potential energy at 2? Wasn't it this? 2.5 times 10 to the 5th. What do you know? Look at that. That's the same number as what we got here. It doesn't matter where we put our coordinate system. I hope that proves it to you. Okay, so that's the end of this video. Bye.